All right, go and take out your speed drill and review exercise booklet. Speed drill and review exercise booklet. And page 22, we're going to work on speed drill 21. Speed drill 21. So last speed drill was just addition and subtraction, real easy. Or a little while ago we did a just division speed drill. We're going to do a just multiplication speed drill now. Speed drill 21, they're on page 22. You'll have 4 minutes to complete the speed drill, and you may begin. My students are finished. You still have over a minute remaining, but we're going to take a look at the answers, so pause if you need to and give another minute. All right, go and put your pencils away, take out a pen. Pencils away, take out a pen. I think the 4 minutes might be a typo. I'm just saying, like, y'all were done in 2.5 minutes. I feel like 4 minutes is a typo. Probably ought to be 3, but anyway. This will help someone who's really, really slow. So maybe like Hayden next year. I'm just kidding. I've heard you're really, really fast. So that's all right. Let's go ahead and grade your own. So pencils should be away. Going across the top row. 65,282. 2,345. 21,350. 1,905,330. 0.0224. 568.75. 0.00024. 1.0396. Do we need to repeat it? All right, these are 12 points each. So minus 0, of course, is a 100. Yes, ma'am.
I accidentally forgot to put like a comma.
A comma? Commas are okay. You can't forget a decimal point, but you can forget a comma.
Sometimes they should put more columns because these are worth it definitely.
That doesn't sound good. Minus 0, of course, is 100. Minus 1 is an 88. Minus 2 is a 76. Minus...
I got 70.
Okay, so just missed the 2 there. Okay, that's not as bad. I was like, oh no, how many did you miss?
No.
Okay, so minus 2, 76. Minus 3, if you're watching and need it, would be 64. Minus 4, 52. Hopefully you didn't miss 4. All right. But how'd you do, Lana?
I
Got 100? Okay, good job on that. And then Joshua, did you see what you did?
Was the bottom one 578.75?
568.75. Do we see that one worked out?
560. Let's see where I started.
Okay, we can take a look at it after class if you need to as well. All right, let me go and collect those from you. And I might, when I go back and check it, I'll probably find in red too, and I can mark it. But yes, right after class, and we'll take a look at it. All right, for now, if you would, want to take out your textbooks, turn to page 406. Page 406. And quickly, let's review some things we talked about in the last couple of lessons. We've been talking about collections of information, class, that we call data. And if the data is numeric, that is to say it's numbers, we would refer to it as
numeric or statistics.
Statistics, right? Statistics would be our numerical data. And with numerical data especially, it's helpful to kind of find what's normal. All these stats and numbers, but what's kind of the normal? For instance, if I told you that a couple of years ago, the Colts quarterback, Jacoby Brissett, threw for 2,900 yards that season, you might be like, wow, that's a lot. Or you might be like, that's not much. Well, how would you know if it's a lot unless you knew what was normal? When I tell you that a typical quarterback in the NFL throws for about 3,600 yards, oh, so he didn't do very good. If I tell you he threw for about 15 touchdowns, well, is that good or bad? Well, typically a quarterback throws for about 20 to 25 touchdowns. Oh, so he didn't do very good. You know, now he only threw for 7 interceptions. Is that good? Well, typically quarterbacks are around 10. Okay, that is good. You know, so you have to know what's normal, right? What do we call different ways in which we can express normals of sets of statistics? There's 3 words. Good measures of center. And there are 3 measures of center that we talked about, Joshua.
Wait.
That's a way of showing some things, but that's not one of the measures of center. They all start with M. There are measures of center. Mean, median, mode, right? Mean, median, and you knew that. Let's rewind. And Joshua, what are our 3 measures of center? They all start with the letter M. Great job, Joshua. And what does mean, Joshua?
Like the average.
Yeah, the average, not just like the average, it does mean average. Yeah. What does median mean? Which one? Just kidding, median. What is the definition of median?
Middle.
There we go, the middle number. Once we put the data or the statistics in order, numerically, least to greatest, we would call that ranking the data, good. And then the last one was the mode, which means?
The one that occurs the most.
The most. Now, one of those you could use even if you didn't have numerical data, even if you didn't have statistics. What we call descriptive data, qualitative data, or categorical data, as the book says. Which of those measures of center can we use for categorical data?
Mode.
Mode, right? Because you can't find a middle of terms or words, right? You can't average words, but you can average numbers. You can find a middle of numbers. So the mode would be really the best use for categorical data. And we showed a way in which we can easily spot the mode by kind of making a graphy type thing. Do you remember what that graphy thing was called? A dot plot. There we go. And very simply, you write down a data point, put a dot. And when it comes up again, you put another dot. If you get a different data name, then you write that down and put a dot for it. And you just make a data plot out of it. Or a dot plot out of it. Looking at page 406, I want you to do number 9, first of all. You're going to take the numbers from problem number 8. We're going to take the numbers from problem number 8, and I want you to rank the data and see if you can find any outliers in that data set. Number 9 refers back to number 8. You're going to rank the data, the statistics there, and circle any outliers that you find. All right, Lana, how did you write the data as you ranked it?
13, 22, 25, 26, 27, 27, 27, 28.
Good. And so let me read that again. Suji did not miss any numbers. She did a good job. 13, 22, 25, 26, 27, 27, 27, 28. And again, the idea there is as you find a number, cross it out so you know that you've used it already. You should end with all numbers crossed out. Any of those outliers, Joshua?
13.
I would say 13 is an outlier. All the other numbers are in the 20s. And if that had been 19, would we call it an outlier? I don't think so. Because 19 would only be 3 away from 22, which is 3 away from 25. But 13 is 9 away. None of the other numbers have a gap of 9 between them. Does that make sense? So that outlier there would be 13. Now, we talked about these different measures of center. Which of those measures of center, if there are outliers present, especially major outliers, I don't know that I'd say 13 is a major outlier, but if there are outliers present, it's really going to mess with the mean, right? So if there's outliers present, really don't want to mess with the mean. What would be a better measure of center if there are outliers, class?
Median.
The median. Good. But if there really aren't a whole lot of outliers, what's the best measure of center? If there aren't outliers, then the mean would be, right? So that's why we normally average things, right? We assume no outliers. Like with your grades, we assume you're going to be a pretty consistent student. Now, if there are outliers, we want them to either help you. For instance, maybe you're a C student and you got 100 on this quiz. Okay, we want that to help you, right? If we gave you your median grade, then the 100 doesn't help. On the same note, if you're an A student, you're a lazy slob one day, you don't study, you get like a 30 on a quiz, well, we want it to sting. But if we were doing median, it wouldn't sting, right? So to make sure that grades are affected properly, we want to account for outliers with grades. But in most average cases, means what you want to shoot for. But if there's outliers, we go with the median. I want you to find the mean and the median now. And let's do that mode as well. We'll lump that in as well. Mean, median, mode there on number 10. So we're going to add mode there. Round to the nearest 10th if necessary. right, what did you get for the mean, Joshua?
24 and 3.
Good, 24 and 3/8, 24.375, or if we rounded to the nearest tenth, like I said, 24.4. What did we get for the median, though, Lana?
I didn't finish that one. Like,
Okay, let's do the median real quick. Again, that's just the middle number. Which number is in the middle?
there's two.
There's two, right?
So-
26 and 27. So what's in between 26 and 27?
25. Wait.
Picture
26 and a half.
26 and a half. There we go. 26 and a half would be in between those two. And obviously, what's the mode, class?
27.
27, right? Even as you were writing it, you were noting the mode would be 27. The best measure of center, probably the 26 and a half. So Coach Cheryl Reeve of the Minnesota Lynx, pretty much you could count on her to get 26 and a half wins. They get a half a win. Well, that's okay. It's just an average. All right. We kind of already talked about number 11. Flip over, if you would, to page 412. Page 412. By the way, we said mode you want to use when you're dealing with non-numeric data, right? What other times might mode be beneficial? What did we say would have to be true of the data set to want to use the mode?
Most, like,
You'd want to have one clear winner, but you really need a data set that is fairly large to matter much, right? For instance, if you ask 10 people how much money do you make in a year, and you get 8 different answers, but a few people say 35,000. Does that mean that's what most people in America make? Well, your sample size is so small, it's hard to know, right? So, but a large sample set, if you're like, hey, I get more people telling me 47,000 a year than anything else, okay, that must be what most, the typical person in America makes. So a large data set would be valuable. I want you to do 24 through 27 on page 412. 24 through 27, they're at the top. Finding mean, median, mode for each situation, again, round to the nearest tenth. And then on the dot plot, shouldn't take you long to find the modes for 26 and 27. Page 412, 24 through 27. Just a little longer, finishing up. Let's go ahead and take a look at this together. Number 24, Rachel plays high school basketball. She's scored certain amounts of points in these various games. Obviously, her best game, she scored how many points, class? 18 was her best game. Her worst game, she only got 4. I don't know if I entirely call 18 an outlier here, because she also had a game with 16, right? So, I mean, it's not that weird. I almost can't consider 4 an outlier because she also had a game with just 7, right? That's only 3 off, which she had a game with 8, games with 9. I mean, 16 and 18 are almost more outliers, to be quite honest, but she had 2 of them. So I would say here the mean might be a really good measure of center because there really aren't any true outliers. And Lana, you said it a minute ago by accident. What is the mean? 10. What was her median score? Yeah, should add them together, and you got 80, I believe, when you added them? Yeah, divided by 8 games?
Oh.
Would be 10 points. What did you get for your median score, Joshua?
9.
And the mode?
9.
Also 9. Right, so those 2 measures of center say 9 should be the normal. The mean says 10. Pick one, right? They're so close together. 9.5, okay? Whatever you want to say a normal game would be.
I got 40 because I divided by 2 instead of...
Yeah, makes sense. Make sure we divide by the number there are. Looking at number 25, tour guide, record the number of people on each tour for a week. And again, looking at this, I do see... I feel like 14 is a bit of an outlier. I feel like 67 is a pretty significant outlier. I mean, that's 15 different from the next one there. Though even 52 is a pretty, so I mean, there's a couple just really crazy high weeks. What did you get for the mean here, Joshua?
135 and a half.
I think you divided by 2 again, instead of dividing by, let's see, 7. Yeah, Lana?
I got 35.9.
Rounded 35.9. So make sure we're dividing by the number of values there. And you know, the good thing though, Joshua, about messing that up is it's going to tick you off and frustrate you so you won't do it on the quiz or the test next week, right? So 35.9 should have been our average or our mean. What about the median, Lana?
34.
34, and obviously class there is no mode. There again, it's kind of all outliers. The numbers are just so scattered. I feel like the mean is probably a good measure of center anyway, and it's not too far off of the median, which kind of reinforces, yeah, 34, 35, 36, maybe split the difference and say 35 is kind of normal for them. And that's the nice thing about having multiple measures of center you can use. Number 26, there is definitely a clear mode, class. 6. Number 27, on the surface you might look at it and say it's bimodal, 2 modes, but really, truly, I would almost argue there's really no true mode here. I mean, it's a pretty flat distribution across the board. I would say 3 is more of a center, even though it's not a mode. So the dot plot kind of shows us how evenly everything's distributed, where in number 26, I mean, it clearly peaks at the 6, a very obvious mode. Questions on the dot plots?
Bimodal.
So one could argue bimodal on 27, that 2 and 4 are the 2 different modes. But again, they're not beating the others by much at all anyway, right? I mean, they barely beat 3, which barely beats 1 and 5. I would almost argue there's no true mode to number 27 because there's not a clear stand out above the rest kind of thing. Does that make sense? So that would be my, again, I'll go back to the illustration. If we're like, okay, Zaxby's, Chick-fil-A, or Culver's. It will abbreviate here, okay? So if I'll use actual numbers here, but if we polled 30 students, and 8 of them said Zaxby's, and 11 of them said Chick-fil-A, and 10 said Culver's, do we really have one that stood out among the rest? No. We have a winner, but does it really stand out among the rest? No. But if we polled it and we had 15 say Culver's and 7 say Chick-fil-A, 8 say Zaxby's, now do we have a clear winner? Yeah, I would say now Culver's is clearly the mode. Technically, by definition, Chick-fil-A would be the mode here. But in such a small data set with such even numbers, I really would argue there's not much of a mode here. Definitely a clear mode with Culver's there. All right, turn back to page 407, excuse me. We've been talking a lot about probability, okay? And what we've been talking about technically is what's called theoretical probability. You see that bold term there. Theoretical probability says this: if there are 3 items on the counter, there is a 1 in 3 chance that I pick that one. Does that make sense? And statistically speaking, mathematically speaking, that may be true. But let's suppose that there are 3 items on the table. One of them is a $20 bill, one is a $5 bill, and one is a $1 bill, and nobody's watching. Which item am I probably grabbing all 3? But if I can only take one, which one am I grabbing? The $20 bill. It's not a 1 in 3 chance that I take the $20 bill. It's a 100% chance. Now, if I'm blindfolded, it's a 1 in 3 chance again, because I can't tell by the feel which one's which. But if my eyes are open, I'm definitely taking the $20 bill. Make sense? If we were to put Lana in a Major League Baseball game, and now pinch hitting for Nolan Arenado, Lana. Anyway, and so she comes up to bat, and we could say, what are the chances she gets a hit? Well, you could say, statistically speaking, there's a 1 in 2 chance. Either she does or she doesn't. No offense, Lana. I do just as bad. She ain't getting a hit. She ain't hitting a major league pitch. Any more than I'm hitting a major league pitch, right? Glenn, maybe has a chance. He's been to the batting cage, I assume, a whole lot. You've cranked up the velocity on that arm a couple times just to see if you could do it. What's the highest you've ever hit?
About 80.
About 80. So you've hit 80. He might have a fighting chance on a 92 mile an hour. Maybe has a chance. Lana and I got no shot. Okay? It ain't happening. Okay? Statistically, theoretically, there's a 1 in 2 chance. But realistically, when you account for how a person would respond, that changes things. For instance, I know this from experience, and this is what we call experimental probability. This is based on observation. Okay, experimental probability is based on observation. Let's suppose Joshua has a choice. Joshua, you can choose Starburst, Snickers, Skittles, and Whoppers. Now, blindfolded, it might make it a 1 in 4 chance. But if your eyes are open, Starburst, Snickers, Skittles, Whoppers, there is not a 1 in 4 chance he's taking Whoppers. I know this because I buy candy for the food drive, right? The candy that we give out, nobody takes Whoppers. I have stopped buying bags of candy if Whoppers are in them because I'm going to have a ton of Whoppers left because nobody likes Whoppers, okay?
I like Whoppers.
Okay, nobody ever takes the Whoppers. I'm just saying. Okay, you got a choice. Nobody's taking it. If I'm golfing, what are the odds I get a hole in one? Whether you do or you don't, right? I don't. I promise you, I'm not getting a hole in one. Even mini golf, the chances of getting a hole in one are not 1 in 2, either you do or you don't. No, it's very, very low. Experimental probability, if you'll note this, is based on observed, recorded data. Experimental probability is based on observed recorded data. So for instance, we'll take Glenn in his Little League, right? Okay. And Glenn, are you a pretty good hitter in Little League? All right. Is there a guy on your team who's better than you? Okay. What's his name? Just first name?
Blaze.
Blaze. Okay. Blaze is who's the worst hitter on the team? Hopefully they will never see this. It's not you, is it? We'll just say it's Glenn for sake of illustration. Okay. Sorry, Glenn. All right. You couldn't give me a name, so we're going to go with you. All right. So it's the bottom of the ninth, and we've got a chance to get the right batter up. Maybe somehow, some way, there's a pinch hit situation, and somehow Blaze and Glenn are both available for pinch hit. There's a reason the coach picks Blaze over Glenn. You know why? He's a better hitter. Based on observation, Blaze is hitting 570, and Glenn's hitting 230. Well, I'm not taking a 230 hitter over a 570 hitter. The one hits the ball 57% of the time. The other hits it 23% of the time. Glenn, based on my observation, has a 23% chance of getting a hit. I don't like that. I like my 57% chance of getting a hit. I'm throwing Blaze out there. Does that make sense? That's experimental probability. It's based on what you've observed. It's based on what we've seen take place in the past. For instance, is it going to rain today? Well, there's a 50% chance, right? Either it does or it doesn't. No, based on what we've observed about cloud patterns and weather patterns, and it's not raining today. Tomorrow, they're saying there's a good chance it'll rain. You know why? Because it's based on weather patterns. It's not a theoretical probability. Well, it's 50% chance either it will or it won't. No, there are other factors involved. Look at the example that they use there. They say that some 8th grader is going to choose a sandwich. They test 30 people, 30 8th graders, and 6 of them say, I would choose a ham sandwich. 15 of them say PB&J. 9 of them say tuna. I am shocked that 9 people said tuna. Y'all like tuna? I will eat tuna. Like, we got free sample of tuna from Walmart, and I ate it, and my wife hated that I opened the package. Okay, but I didn't want it to go to waste. I hadn't had tuna in a while, so yeah, I'll try it. It was ranch-flavored tuna, whatever. It's all right. I wouldn't buy it. Okay, I don't think 9 out of 30 8th graders are picking the tuna, all right? But you know this. If it's those 3 options, it's not 1 in 3 chance that a kid, especially even if they're blindfolded, because they can smell the tuna and stay away from it, okay? There is not a 1 in 3 chance they're taking the tuna, okay? Most 8th graders, at least when I was an 8th grader, I like PB. I still eat PBJ every other day. Like, I mix it up. I do ham sandwich one day, PBJ the next day, just for variety. It's not much variety, I know, but whatever, okay? That's my lunch every day. I still eat PB. I like peanut butter and jelly. I don't care. But again, that's based on observation. And notice they set up what's called a frequency table with it. A frequency table is basically just a list of what people prefer. They set it up 2 different ways. Notice one is horizontal. They list the people who wanted this, this, and this, and they give you a total. And then they set up a frequency table vertically. This, and this, and the total underneath. Doesn't matter which way you choose to set it up. It can be vertical, horizontal, doesn't matter. It's just a table listing out how many people picked what. Make sense? That's a frequency table. Now, a relative frequency table, relative frequency, by the way, I want you to jot this down in your notes. Relative frequency is the probability of an event occurring. Relative frequency is the probability of an event occurring based on past history and observation. Relative frequency is probability based on past history and observation. It's another form of probability, but it takes into account that people have the ability to make choices. Blindfolded reaching into a bag, what marble do you choose? It's random, right? That would be theoretical probability because it really is truly random. But if you open the bag and you have a favorite marble, what are the odds of picking that marble? That's the one you're going to pick every time if you like to play marble. I had marbles when I was a kid. I don't know if y'all ever had marbles, but I had the favorite marble. I really liked this one. I thought it looked cool. Had a little design going on inside. And so you have something that's favorite, you're obviously going to pick that. That's based on past history. That's relative frequency. Now notice the way they set up the relative frequency table. Do you see that it mostly looks the exact same except the numbers, right? The numbers are different. They divided, ham is 6 out of 30, right? 6 to 30 is 0.2, okay, or 1/5. PBJ is 15 to 30, that's 1/2. 1 to 2, that's 0.5. Make sense? And then tuna's 9 out of 30. That's 3/10 or 0.3. And notice that the relative frequencies add up to a total of 1. Probability still has to add up to 1. Does that make sense? How to set up a relative frequency table from a frequency table. You divide the number of choices by the total in every case to get the relative frequency. Questions? Let's flip over a couple pages then. Correction. Flip over one page. And let's look at another example here. Okay? So 12th graders. 12th graders were asked about their sandwich preferences. There were 40 of them this time. You see that? This is in the paragraph. There's not a cool table for it. They didn't set up a frequency table, which would have made life really easy. Let's set up our own frequency table. All right, so we got 12th grade. All right, and they're also choosing what kind of sandwiches they want. We know there's a total of 40 of them. And it's the same choices: ham, PBJ, and tuna. All right, and of them, it says that 10 of them like the ham sandwich. Now, I will say, ham, if that's all that's on a sandwich, it's kind of sad, right? Or even with that, like, American cheese, fake cheese, single stuff, not a fan. I'm not eating that sandwich. But, like, you get a nice cheese, like provolone, Munster, Colby Jack, Gouda, Havarta, a nice cheese that tastes really good, very flavorful. And I like to put a little salami on there just to get a little extra yummy flavor. Salami is a type of sausage, really flavorful. It's great. Then I'll eat the ham sandwich, okay? But just plain ham, I'm probably not picking it either. 16 with the PBJ and 14 with the tuna, right? So I know. Maybe they have more sophisticated tastes. Anyway, this allows us to compare 8th graders with 12th graders because we can now set up a relative frequency table. To figure out how many people want ham, what do we have to do, class? What?
10 to 40.
10 to 40 is
25%.
1 to 4, 25%, 0.25, right? Okay. PBJ is 16. Now divide it, reduce it by 8. What does that reduce to?
2 to 5.
2 to 5, which is 0.4.
Which is 40%.
40%, 0.4, right? And then 14 to 40, all we can do is reduce by 2.
7 to 20.
7 to 20. Now I'm going to then multiply both by 5, right?
Yeah.
And that'll give me 35 to 100, which obviously is 0.35. Notice they add up to 1. Now the other way you can cheat the system is you know they have to add up to 1, right? So if you know you got 0.25 right, look in Lana, if you know you got this one right and this one right, you can subtract from 1 to figure out that number instead of having to do this math. All right, so 25% of 12th graders are in on the ham, but looking back at the last page, only 20% of the 8th graders. So there are more 12th graders who like ham. 40% PBJ to 50%. 8th graders like PBJ more, and 35% tuna to 30% tuna. Slight win for the 12th graders liking more tuna. But you see how you can even compare different groups based on their relative frequencies. Okay. Questions on relative frequency? Look at example 8.8. Go and read the blurb for us there underneath the bold text, Joshua. Where it says shoppers were surveyed. We're on page 408, example 8.8 in a yellow box. Example 8.8, it's a yellow box.
I thought you said A.
Sorry.
Shoppers were surveyed to determine their flavor preferences for potato chips. Out of those surveyed, 17 preferred barbecue, 14 preferred plain, 8 preferred cheese, and 11 preferred some other flavor.
All right. Notice what they did first. They create a frequency table. That's literally just listing out all the numbers people that they had, right? Now, they divide all of them by 50, which is really smart to use 50, right? Yeah, just double to get 100. So 17 is double that, 34%. 14 is 28%. 8 is 16%. 11 is 22%. Notice it all adds up to 1 when you add it all up. And we make a relative frequency table. Questions on that? All right. Now turn over to page 410. Turn over to page 410. Now, I want to start by getting you to think here, theoretical or experimental probability. Remember, theoretical probability is you're blindfolded, you don't have a free choice, it's just up to the numbers. Experimental is, based on what we've seen, people tend to respond this way. Okay, so number one, a spinner with sectors labeled 1 through 6 is used to see how far a player moves on a board game. What's the probability of spinning a 4?
Theoretical.
That's definitely, yeah, it's up to random chance, isn't it? Okay? Number two, children are asked about their favorite vegetable. What is the probability of a certain child choosing broccoli?
Experimental.
That's experimental, right? We kind of have an idea of how this kid's going to choose if they've got that choice. A blindfolded student pulls a marble from a bag containing various colors of marbles. What's the probability of the student pulling a yellow marble? We're back to theoretical again. Do you see how blindfolded doesn't have that freedom to make the choice? It's just up to the theoretical probability. So all the probability we talked about up till today has all been theoretical. Now we're going to deal with the real choices. Look at number 4. For the last week, Elijah observed the types of sandwiches his coworkers ordered for lunch. The sandwiches included 6 egg salad, 20 ham, 10 tuna, and 24 turkey. I guess you can't order peanut butter and jelly at the restaurant. You know, I have never seen peanut butter and jelly at the restaurant. Anyway, so fill in the frequency table. Don't make this too hard. You're like, I feel like there's a catch to this. Nope, it really is this easy. It's like it knows you're tired here in the third quarter and just need a brain break. The only math you have to do, class, is the total. Yeah, you just fill in everything. 6, 20, 10, 24, and what's the total, class?
60.
60.
Oh, 4, 5, and 1.
Yeah, okay. 60. Now the good news is 6 to 60 would reduce down, wouldn't it? 1 to 10. 20 to 60, 1 to 3. 10 to 60, 1 to 6. 24 to 60, 1 to 5. Right? So when you could, or 2 to 5. You can reduce all of those very easily and get your decimals. If we wanted to. We don't. Number 5. Fill in that box. Students wrote English papers on classic authors. The following authors were used. 35 students chose Dante, 10 chose Homer, 25 chose Milton, and 30 chose Shakespeare. I would not have thought that many would pick Dante. Considering I don't remember very many things he wrote. Setting up the frequency table. And on a frequency table, the only math you do is the addition. All right, hopefully you wrote Dante, 35, Homer, 10, Milton, 25, Shakespeare, 30, total 100. All right, you did that?
Yeah.
All right, let's look at the next thing. Now, we've got a frequency table. Now we want to set up the relative frequency table. They have tourists from different states coming through, and some from Alabama, some from Colorado, some from Massachusetts, some from Wyoming. That's what those different letters stand for. What we've got to do is figure out what is the relative frequency. Now, Alabama should be pretty easy. So write AL and figure Alabama's relative frequency. What do we get?
0.25. I mean, wait.
0.1.
0.1, yeah.
0.1. 440 is 1/10 is 0.1. Colorado should be also very easy. And what do we get, class?
0.5.
0.5. Right, 20 out of 40 is 0.5. The next one's a little bit more obnoxious. Massachusetts.
Of course.
Gonna have to do a little division here.
Wait. It was just point.
For Colorado, it was just
Yeah.
0.5. Yep. Massachusetts is going to take a little division. Call it when you've got it. you get 0.075?
Mhm.
All right, and then the next one is
Oh, so-
Wyoming, 13.
You're not doing any rounding?
Nope,
Oh.
because we need it to add up to exactly 1.
Oh.
So if we were to round, it would mess up the addition.
Yeah.
So we're fine. So you have to do it.
Or I guess you could add them up and subtract from 1. We could do that way as well. Or we use the division method. And get 0.325. 0.325. All right, insect collection. Now,
Wait, what's the total?
Yeah,
Oh, 1.
the total has to, it better be 1. If it's not 1, we're in trouble. It is 1. The total has to be 1 because the total of all probabilities always adds up to 100%. Insect collection. 100 people picking different, or I guess 100 insects in the collection or something. I don't know. Anyway, isn't it nice they said 100?
Oh, yeah.
Bless them. So what's ant, class?
0.32.
Good. What's beetle, Lana?
Wait. Oh. I feel like it's 0.9. Wait, 29.
20 to 100.
0.2.
0.2.
I was thinking.
All right. So what about butterfly?
0.18.
0.18. What about fly, Lana?
0.22.
0.22. And then mantis?
0.08.
0.08. And of course the total class is 1. Next page. Now we're going to do the whole thing. All right, so we've got all these different desserts. Okay, we've got 65 people chose gelatin. Go and write that in. That's like Jell-O. Okay, 65 people chose gelatin. That doesn't even sound good. 35 people picked cobbler. That sounds good. I like cobbler, though it's going to be more expensive than gelatin. 40 people picked ice cream. I like ice cream. I like ice cream with cobbler. And 60 people picked pudding. See, I'm not a pudding or gelatin person, but I like cobbler and ice cream. Anyway, so fill in the frequency table first. So, big thing we gotta find is the total. All right, what's the total?
200.
200 people total. All right, now think about that. If 200's the total, we can make it to 100 if we just cut every number in half.
Yeah.
So for gelatin, it's not going to cut in half evenly, but what is half of the 65?
Wait, how does
2 goes into 6,
3 times.
2 goes into 5,
No,
2 times with a half left over, so 32 and a half. But again, we got to make it that decimal 0.325. You see what we do? So to get 100, we cut it in half, and then we just move the decimal place, so 0.325. Let's jump to ice cream. What would ice cream be? Let's drop down to ice cream. What would ice cream be?
17 and a half?
I said ice cream. Drop down to ice cream.
Oh, ice cream.
It's 40 to 200, right? Divide both of them by 2. That's 20 to 100, so obviously it's
Oh.
0.20, right? 0.20.
Oh.
Because hundredths, 2 decimal places, okay? What about pudding at the bottom of the list? What's pudding?
0.30?
0.30. And then cobbler, this is where Joshua already did this one. He saw this is 17.5 hundredths, right? When you divide both of these by 2. So, 0.175.
Oh.
Right? 2 goes in 1 time, 1 left over, goes in 7 times, 1 left over. So 17 and a half, 17.5. So cutting numbers in half can help you get those. So, letter A. What's the probability that the next person chooses ice cream based on these numbers?
Well,
20%. Didn't you just write down that ice cream is 20? Again, and it's not 1 out of 4. It's because ice cream isn't being chosen 1 out of every 4 times. So based on what we've observed, the probability of ice cream is only 20%. What's the probability of gelatin or cobbler? I have to add them.
50%?
50%, 0.5 when you add those together, right? And or means you add. 0.5 is 50%.
Oh.
Yep. It asks, what was the total number of people that got dessert? 200. And if the restaurant only expects 100 people to take dessert tomorrow, and again, this is where they have to make decisions. The restaurant's like, okay, tomorrow's not a heavy day. Probably only 100 people come in to get dessert. How many of them are probably going to get pudding? 30. We expect 30 people. So let's prepare enough pudding for 30 people. And that's how they can make their estimates. It's not, well, if we expect 400 people and we offer these 4 desserts, we better have 100 of each. Well, if nobody likes the marmalade, whatever, the pistachio pudding, then don't make 100 servings of pistachio pudding, especially if everyone's getting your Rocky Road ice cream. You know, so they base their decisions not on true or theoretical probability, but on experimental probability. Homework for this evening. Homework for this evening is to be pages 412 to 413. Pages 412 to 413, numbers 1 through 16. Now, we have not talked about 13 through 16 yet. So I just want you to see if you can figure it out. If you don't, that's fine. You don't even have to read, but I think you're smart enough, you'll figure it out, and you'll realize, oh, tomorrow's lesson is going to be easy. It's the kind of questions, by the way, you would see on standardized testing that you normally wouldn't have learned before. You're supposed to be able to think and figure it out. So I want you to try those 4. Think. I'm telling you to think because it's an important life skill. Think on 13 through 16. Don't go back and try to look it up. If you look it up, you'll get confused. Figure it out without looking anything up. Okay? 13 through 16 is that way. 1 through 12 is straightforward. 13 through 16 you're going to try. Test 8 is in lesson 128. Next test coming up in lesson 128. That'll be on Tuesday. Test coming up over chapter 8. All right, have a wonderful rest of your day.